Okay, so if you remember on Thursday, we had this question that we were looking at the RL circuits. Here we had our inductor, and we had some resistor. We were looking for the equation that would describe how the current would change in time. So we just assume that somehow we start a current to run in the circuit, and then we just remove that effect, and how does the current change? The correct equation was this one. I times R plus L di by dt, this should be equal to 0. This was the correct equation. Now, to obtain this equation, there were many means of obtaining the same equation, and in one of them, if you remember, we were just imagining that we had some unit positive charge, and we were carrying it around this loop. And when we said, okay, so we take this positive charge, we just move around this loop in the counterclockwise sense, and we calculate the work that we had to do. Now, in that case, we had assumed that, okay, if we go across the resistor, then we have to do a work I times R. And if we crossed across the inductor, we had this reasoning. Okay, it has to be the L di by dt by some, it might be positive or negative. Just to fix the sign, we just assume that, let's assume that I is increasing in time. So if I is increasing in time, then this inductor will try to prevent that change. So the inductor will be pushing charges from right to left. So we have to do work as we are moving this positive charge over the inductor is already pushing the charge in the direction that we are moving. So we have to push the charge, exert a charge on the force that on the charge on the opposite direction. So we are, if di by dt is positive, the work that we do would have been negative. And this was equal to 0. So these were the two equations we obtained. And we said that this equation is definitely wrong, but what is wrong in our reasoning? What is our mistake? Any thoughts on that? Why is this wrong? So we calculated the work that we have to do if we are going around the circle in one closed loop. And since when we reach this point, the charge has the same potential, the same kinetic energy, so the work done on the charge should be 0. So, and using that reasoning, we have this minus sign over there, which is definitely wrong. Any ideas, any thoughts? So we have to do some work against it. This is it, this one. That is this one. The dissipation is in this term. Now, the difficulty is this one. You see, we have this equation. We have this equation. Now, in the second one, our reasoning was this. We hold some positive charge and move this positive charge in one closed loop. Okay? Now, if we don't give it any acceleration, then the force that we should exert on this test charge is minus QE. This is the force that we have to exert. Q times E is the force exerted by the electric field. If we want to move it around with 0 acceleration, then we should exert this much force so that it will have 0 net force and hence 0 acceleration. Now, the work done as we move this charge in one closed loop is this one, whatever the loop is. So this is equal to minus Q E dot dl over one closed loop, which is definitely not 0. So here we claim that this is the amount of work that we have to do, and we set it to equal to 0. This is L di by dt. It cannot be 0. So we have, if we take this charge and move it around, we have to do some non-zero work. Now, of course, since the charge is not getting any acceleration, etc., the work that we have done should be dissipated somehow. Now, the work that we have done per unit charge, it is minus E dot dl. And this has to be equal to minus L d minus I by dt. Now, why minus I? Because mainly we are going in this direction. We are going around the loop in that direction, so we have this minus I. Now, this is the work that we do, but this work has to be dissipated somehow. And the dissipate, how much per unit charge, what is the energy dissipated would be is just I times R. This is the amount that we have dissipated. Sorry, we have another minus sign. Now, what are all these minus signs? This minus sign is this one over here. These two are equal. This minus sign is from the Faraday's law, is minus L di by dt. And this minus sign is because our current is running in the opposite direction. So this is the work that we have to do if we want to carry this unit charge around the circle. And it has to be the power dissipated by the resistor. IR is equal to minus L di by dt, and hence we again reach the same equation. You see, this is the work that we are doing on the charge. This, if there's no dissipation, the charge should accelerate. But we know that nothing changes, the charge is not accelerating. So the work that we do has to be dissipated. So this is the amount of work that we do. This is the amount of work that we do. This is the amount of energy power dissipated. So they have to be equal. Which one? This one? Yes. Yeah, energy dissipated. Sorry, it's not the power, energy dissipated. Per unit charge. This is basically, okay, I will still say that this is the potential difference across the resistor. I mean, when you have changing magnetic fields, you cannot really talk about potential differences, because potential difference, if you calculate the work done will depend on how you go from one point to the other one. But as long as you keep away from changing magnetic fields, as long as you don't consider a path that goes around your inductor which contains your changing magnetic field, you can still talk about potential differences. Anyway, this is just one of the means of obtaining the equation. I would advise to stick with the other ones. This is probably the most complicated one. Any other questions on any questions on anything that we have done? And we will do more examples on determining the sign of this L di over dt term. No. This equation is completely wrong. Our reasoning in this equation was completely wrong. We were saying that, okay, this is the work that we have done on our charge. It shouldn't be zero, the work that we have done. I mean, even if this is the work that we have done on our charge, it shouldn't be zero. That is one thing. The second thing is, this term by itself is the work that we have to do. Now, it will be simplest if you just calculate the work done on the charge. And that should be equal to the energy lost by the charge. Any questions on this? Or on the things that we have done until this one? We will do more examples on this before we continue. Well, let's just add a resistance. Now, we already have a, okay, so the examples that we had discussed until now. We had an inductor, an RL circuit, an inductor and a resistor. We have an inductor and a capacitor. We already had studied capacitor and the resistor. Now let's put all of them together. We have a resistor, a capacitor, and an inductor. And by some means, at some instant, we just started a current running through the system. Now, how we can do that? For example, you can just imagine that this is, in fact, it was initially part of another circuit. And we started with this is the initial circuit. We start with switch at this position. And here there is some, let's say, capacitor, some power supply. And you can just, you charge the capacitor. This is nothing but at this, when the switch is in this position, this is nothing but an RC circuit. You are just charging the capacitor. Once the capacitor is charged, then you just move the switch to here. Then you are basically disconnecting this power supply, and you just create some, the capacitor is initially charged. So these are your initial conditions. You have some initial charge on the capacitor. The current at t equal to 0 is equal to 0. Or you can just switch the, move this switch to this position before the capacitor is fully charged. In that case, you would also have some initial current, you would have some initial charge on the capacitor, etc. So you can get a configuration in which at a given instant, there will be some current running in your circuit, and the capacitor will be charged. Now, let's first choose the positive and the negative plates of the capacitor, and let's say that at this instant, we just have Q of t. So at this time, we have a current running through our system, and we have a charge going over our system. So what is the equation that will govern the time dependence of the current and the time? What are the equations? Now, first of all, with this convention of the positive sense, so if the current is positive, is the charge in the capacitor increasing or decreasing? If I is positive. So if I is positive, with this convention, the charge, if I is positive, Q is increasing. So dQ by dt is equal to plus I. Now, for example, we could have as well chosen the positive sense of the current to be the other way around, or we could have chosen the polarity of the capacitor the other way around. We could have said, okay, this is the negative plate, this is the positive plate. In both of these cases, we would have a minus sign over here. But just for these choices, we have this plus sign. Now, what is the equation? This is R, this is L, this has capacitance C. Okay. Good start, the I times R. We have I times R, Q over C, L di by dt, and we will get an equation which will set this to equal to 0. Now the thing is plus or minuses. Which one is plus, which one is minus? Both of them plus, Q over C minus, minus plus, how, I mean, of course, for each sign, since we have two choices, it's 50% chance to get the correct answer. But what is the reasoning? What is this I times R? Potential difference between these 2 points. Which point minus which point? So, okay, let's say that I is positive at this instant. So this is this point at a higher potential than this point or at a lower potential than this point? Okay, this one is smaller. Well, the current runs from a high potential to a low potential. So you can say that we took a positive charge. We are looking, as we go around, we are looking at the change in its energy. So I times R, positive. It lost I times R, this much energy, as it went from this point to that point. This much potential energy. Now, from this point to this point, what was the change in the potential energy? Positive or negative? This is the potential drop as we go from the I times R is the potential drop that we go from this point to this point. Now from this point to this point, do we have a potential drop or a potential increase? It's a drop because positive plate is at a higher potential. So again, it's a potential drop. We are writing the potential drops, so it is positive. Now, the most difficult part, probably, is this positive or negative. Well, we can, let's see. Your friend is saying that the current will be negative, fine. So the current is dropping, so the I by dt is negative. Okay, let's determine the sign for the case the I by dt is less than 0. So is there if the I by dt is less than 0, so does the inductor try to force the current in the counterclockwise sense or in the clockwise sense? So it will force it in the counterclockwise sense. So if you use the analogy that this is like a battery which is pushing the current in this sense, so this will be the negative terminal. This will be the positive terminal of the battery. Now, if we go from here to here, we are going at a higher potential. If we are going to a higher potential, the potential drop should be negative. But we already know that it is L di by dt, but this is already a negative number. So we are just adding this negative number. So this is the equation that determines how the current changes as a function of time. Well, of course, you can replace the current here by this expression. The current is nothing but the derivative of the charge. So 0 will be equal to L d squared q by dt squared plus R dq by dt plus q over c. Now, any questions on this one? How do we determine the signs? Okay. So here, in order to determine the sign of this L di by dt term, we kind of used a trick. Now, what we did was, okay, for one particular choice of di by, now, you see, this equation is valid whether di by dt is less than 0 or greater than 0. In any case, we will have, in both cases, we will have this equation. Now, to determine this sign, we just looked at a special case. Di by dt is less than 0. This is just a special case. If we determine the sign in the special case, the sign will be valid in all cases. Now, what we did, di by dt is less than 0. Let's just assume that at this instant, di by dt is less than 0. Now, we know what the inductor does. The inductor doesn't like changes in the current. It tries to keep the current constant. It will try to keep the magnetic field constant. And hence, it will try to keep the current constant. Now, if the current is decreasing, the inductor will be pushing the current in the direction that it is running. So if the inductor will try to push the current in this direction. Well, it is just like a battery in this sense, because you know the battery pushes the current from the positive terminal to the negative terminal. So this is just like a battery, and if we use this battery analogy, it is pushing the current from the positive terminal to the negative terminal. So it behaves like a battery in which this point is the positive terminal and this point is the negative terminal. But we know what the battery does. It just takes electrons at a lower potential and gives away electrons at a higher potential. Takes charges at a lower potential, positive charges, and gives away positive charges. Takes current, let's say, from the negative terminal and gives away current at a higher potential at the positive terminal. So if we are writing this equation, if we are writing the potential drop of the charge, as we go from here to here, the potential is increasing because this point is at the positive terminal. But if the potential is increasing, here both of these terms are the potential drops. So we have to write a negative potential drop as we go from this point to this point. Now, L di by dt is already negative because di by dt is negative. So this term is negative. So by adding this term, we are writing a negative potential drop. Now, we can do it the other way around. If we assume that di by dt is positive, that is, for some reason, the current is increasing at this instant, then this inductor will try to prevent that. It will try to run a current in the opposite direction. So this side will behave like the positive terminal of a battery, and the other side will behave like the negative terminal of a battery. Then since we are following the potential drop of a given potential drop as we go in the counterclockwise sense, as we go from this point to this point, there is a potential drop, a positive potential drop, whose magnitude is L di by dt, but this is already a positive. So as we go from this point to this point, we have this positive potential drop. So in both cases, we have this plus sign. So although we are determining the sign using some special cases, the sign is valid in all cases. In any case, this is our equation. Now, the mathematical part is how do we solve this equation? Now, you see, when we were discussing RL circuit, no, not RL, LC circuits, so this was our equation. And we had already solved that Q is some Q0 cosine omega t plus delta. I is Q0, no, let's say sine Q0 omega cosine omega t plus delta. We already had discussed these solutions. And we also calculated the energy stored in the magnetic field. Do you remember the expression? Let's say the maximum value will be 1 over 2 L omega squared, Li squared, which is Q0 squared, omega squared, and energy stored, the maximum value of the energy stored in the electric field was 1 over 2 C Q squared. But also remember, omega is 1 over LC, omega squared. This was the omega. So it's basically making an oscillation. The energy just goes from the stored in the capacitor to the magnetic field, and then from the magnetic field to the capacitor, just like in a pendulum. If you remember the mechanics course, what we had in a pendulum was, okay, if this is our pendulum, here it has maximum potential energy, zero kinetic energy, zero potential energy, maximum kinetic energy, and the energy just exchanged between the kinetic and the potential energies. If there were no friction forces, then this just went on indefinitely, just like in here. In this case, it's not the mechanical and the kinetic energy, it's the energy stored in the electric field in the capacitor and energy stored in the magnetic field. Now, the magnetic field just behaves like the mass inertia. It doesn't like changes, where the electric field tries to change things. So in this system, since there is no resistor, there is no energy dissipation, energy just oscillated from magnetic to electric, from electric to magnetic, back and forth. So if you would plot, let's say, electric energy as a function of time, this is the energy stored in the electric field, and this will be the energy stored in the magnetic field. The sum will be always constant. And just like the Q and I, it will be oscillating from the maximum value to 0 and back up. Now we will turn on the friction, in this case the resistors. Now the power, the energy loss in a resistor, this is I squared R, if you remember the power dissipated through a resistor. And due to this I, there will be some energy loss, and hence one thing, energy will not go from this maximum value to 0 and back up again, and hence the Q and I, they will not move between, Q will not be moving between Q0 and minus Q0, but it will just decay in time. Let's say this is Q as a function of time. This is plus Q0. This is minus Q0. this is how it will behave. Eventually, of course, it will go to 0. The same will hold for the current. If you would plot current as a function of time, it will also, in the absence of friction, it will just move from this value to this value back and forth, but when there is the friction, it will just decay. So this will be how it will behave. Now the frequency of this, okay. Now let's give a break now, and after the break we can continue.